both with Brubaker Associates. Jim is a managing principal at Brubaker. He's a registered professional engineer, had an extensive career as Director of Revenue Requirements with Detroit Edison before joining Brubaker. Ali is a senior consultant with Brubaker. He's an economist. He has experience with the Public Utility Commission in Texas, an economist and policy advisor, and has an extensive amount of experience in competitive procurement and rate design issues. So with that, I'm going to hand it off to Jim and Ali to get us started today.
Hello, everybody. This is Ali. I'm going to be starting out the presentation, and the way we've set this up is I'm going to take the first segment of the presentation and go through some slides that discuss the purpose of the study that we conducted, and also provide some background information regarding the structure of standby rates and the various components of standby rates, and some of the best practices in standby rate design that we identified in the course of the study. And then I'm going to turn it over to Jim, who's going to go over some of the details of the specific tariffs that we analyzed and some of the recommendations we developed for those specific tariffs. So just to go over the purpose of the study, we conducted an analytical assessment of the rates, terms, and conditions for standby service. And the focal point of the study, as the title suggests, was on combined heat and power applications. So we were looking for ways to enhance the rate structure and the terms and conditions of standby service in a way that would improve the efficacy and opportunities for deployment of combined heat and power applications. And so we went through a process of identifying specific standby utility tariffs that we focused on for review, and then we identified opportunities for improvement both in the rate structure and the terms and conditions of those tariffs. And once we had done so, we conducted economic analysis to estimate the impact or the quantitative impact of our recommendations in terms of opportunities for savings and economic adjustments to the tariffs and what their impact would be. And in doing that, we focused on a particular representative sample of combined heat and power customers. And Jim will go into more detail later on in terms of how we developed the representative customers that we examined. Next slide, please. So to go over the, just to provide some background information on standby service, standby service is essentially a set of electric utility products that customers purchase when they have on-site generation that serves a portion of their own power needs. And essentially the purpose of standby rates is to provide a backstop for the on-site generation. So if the on-site generator trips either for a forced outage or it has to go down for maintenance, that customer would need some source of power to replace the generation that otherwise obtains from its on-site generator. And the standby service would kick in to provide that backstop. And clearly, standby service is important for combined heat and power applications because it has a big impact on the economics of those applications. If the rates are too high, it creates a disincentive for those types of applications. And also if the terms and conditions of the service are too onerous or burdensome, then it can make it more difficult to deploy those types of applications. And it might make it more attractive for customers to instead just rely on full requirements service from the local utility or purchasing power from a competitive supplier where that option is available to them. Next slide, please. So this slide is a graphic that basically provides some background on the types of purchase requirements that a customer with self-generation would have. And so the white line on the graph is intended to show the customer's overall load requirements over time. And the yellow line you see on the graph is intended to show the customer's generation requirement, or the generation that's being produced by its on-site generator. And so the difference between the white and the yellow line is shown by the green shaded area. And that green shaded area can be referred to as the customer's supplementary or supplemental power requirement. And that's essentially any power that's taking in excess of the capacity of its on-site generation. And And that's power that the customer would be taking from the local utility on a continuous 24/7, typically firm basis. So it's essentially indistinguishable from full requirements power that a customer without on-site generation will be taking from the utility. Now you see there's two red shaded areas that are on the graph. The red shaded area to the left is labeled as backup power. And in this instance, what's happening is the customer is experiencing a forced outage of its on-site generator. So, for example, the generator might have a tube leak or other type of unexpected issue that arises that causes the generator to go down. And in that instance, the customer is taking standby power in the form of backup power from the utility, as that service is defined. And backup power is the type of power the customer might need to take at any point in time, because a forced outage clearly could occur at any point in time of the day or any time of the year. So it's something that the utility would need to be prepared to provide at any time across the day or the year. And then you see the red shaded area to the right of the graph is labeled maintenance power. This is power that the customer would take to replace the generation normally provided by its on-site generator when that generator goes down for planned maintenance. So an on-site generator is just like a utility power plant. It's going to need to go down periodically for maintenance. And the distinction between the maintenance power and the backup power is that the maintenance power is a planned outage. So it's something that the customer is going to schedule in advance with the utility, and the utility will try to coordinate that outage in a way that it doesn't conflict with outages that the utility itself is, when it might be taking down its own large base load generating plants, for example, and we'll also try to schedule those during off-peak periods when demand on the utility system is not that high. Next slide, please. So just to go over the typical rate structure, standby rates that you would expect to see, obviously there can be variations on this theme, but the essential components of the rates are, number one, capacity reservation charge. This is a charge that the utility would collect. It's a demand charge that you would pay every month of the year, regardless of whether you're actually taking standby power from the utility in any given month. As long as you're on the standby rate, you're going to be paying that capacity reservation charge, and it's basically designed to compensate the utility for the cost that it incurs to make generation available to you to provide that backup power when you have a forced outage at any time that you might have it during the year. The second component of the standby rate structure you'd expect to see are as-used capacity and energy charges. And so these are charges that you would incur in a particular month when you actually experienced an outage of your self-generator. When you have the on-site generation actually go down, the utility is going to want to be compensated for the cost of the power and the energy that you're actually consuming to replace your on-site generation. So those charges would be used for that purpose. You'd also expect to see, in many cases, a separate maintenance capacity charge. And that's a charge that you would incur during months when you have a maintenance outage of your on-site generator. And as we'll discuss a little bit later, there can be distinction between that charge, the level of that charge, and the charge that you would pay for backup power that you actually take. And then finally, you could expect to see facilities charges, and these are charges that the utility would assess to recover the cost of any dedicated distribution facilities or substations, for example, that it might construct specifically to serve a particular customer that's taking standby power. Next slide, please. So in the course of conducting our study, before we dived into looking at the specific utility standby rates and developing recommendations for those rates where they could be modified, we relied on our experience, and that's to say the Regulatory Assistance Project and Brubaker Associates, put our heads together and tried to develop a set of best practices based on our experience with standby rates to try to use that as a template or a paradigm that we could apply to the specific rates we are examining in the process of developing recommendations for improvements to those rates. So I'd like to spend a little time going over the best practices that we identified for standby rates. The first principle is several sets of points with regard to the allocation of utility costs. First principle is that generation, transmission, and distribution charges should be unbundled in standby rates. And that achieves several goals. Number one, it provides greater price transparency for the customer. It also makes the allocation of the utility costs more precise by separating the costs out into these three distinct bundles. And the third thing that it gets you is it creates a better environment for customers who have an option to purchase standby power competitively, so that if they are looking at purchasing standby power from a third-party competitive supplier, if the generation bucket is unbundled, it's much clearer what costs that the competitive supplier would be intending to replace a rate structure such as that. The second point in terms of best practices with regard to allocation of costs is that the generation reservation charge that we discussed earlier, the capacity reservation charge, should be designed based on the utility's fully allocated embedded cost to serve the customer times the forced outage rate of the customer's generators on the utility system. And the reason that makes sense from an allocation standpoint is that the forced outages are random events, as we discussed. So when an on-site generator goes out, it could take place any time of the day, at any time of the year. The only reasonable way of estimating the probability that those outages are going to occur is to look at statistically what the forced outage rates of these on-site generators are in the utility system. And that gives you a sense of what the reasonable allocation of the utility's fully allocated embedded cost of providing generation service to those customers ought to be. And so if you combine the forced outage rate with the overall embedded cost of capacity, then you get a reasonable allocation of those costs for designing the generation reservation demand charge. And the third allocation principle relates to the fact that higher voltage delivery charges should recognize load diversity. And the reason for that is that the higher voltage facilities such as transmission lines are further removed from the end-use customer than, say, local distribution lines. And for that reason, those higher voltage lines are going to be designed in a way that is designed to meet the capacity associated with customers' coincident peak demands. So you're going to be looking at coincident peak on the system when you're sizing those facilities as opposed to the sum of the non-coincident peak demands of all the customers. And so when you're allocating costs to develop these higher voltage delivery charges, you should focus on the coincident peaks, and to the extent possible, you should also try to use the coincident peak demands in the actual rate design of those charges. Next slide, please. The next thing we examined and identified in terms of best practices for standby rates was that the rates should be designed in a way that provides appropriate incentives for customers to behave in a way that minimizes the cost of standby service on the utility system, in a way that also recognizes appropriately the costs that customers impose on the system when they're taking standby service. So one principle we identified was the notion that you should develop prorated daily demand charges for the points in time when the customer is actually taking standby service. And so essentially what you could do is you take the demand charge that would normally apply to full requirements customer, you prorate that on a daily basis across the month. And in that way, you apply those charges to customers that are taking standby service. The more days that they actually are taking standby, the more that they're paying. What that gets you is you set up an incentive where a customer that has on-site generation has an incentive to minimize the frequency and the duration of their outages. So more reliable generators will pay less, less reliable generators will pay more under a standby rate structure of this nature. The second point with regard to incentives is the daily maintenance demand charges should be discounted relative to the demand charges that apply to instances where the customer is taking backup power to support a forced outage. And the reason for this, as I discussed earlier, is the fact that maintenance outages can be coordinated with the utility, and they'll typically be scheduled during off-peak periods. And for those reasons, the utility's cost of providing maintenance power is lower than the cost of providing backup power, and that lower cost should be reflected through a discount for the maintenance component of the demand charges. The final best practice principle relates to customer options and customer flexibility. So what we tried to do is to set up or make recommendations for standby rates that would provide additional flexibility to customers, give them more options in terms of how they structure the service. And so one way that can be accomplished is providing an interruptible standby service option. And so a typical standby rate would be set up on a firm basis where the utility is required to provide backup power in the case of a forced outage of the on-site generator at any time that outage might occur. The distinction with interruptible service, if you give the customer that option, the customer could choose to take a rate with a lower capacity reservation charge, or even have that capacity or reservation charge eliminated entirely if in exchange for that the customer is willing to forego the firmness of that backup power, so that if the utility is in a situation where demand on the system is very high, say on a peak summer day, it has some forced outages of its own baseload generating units, so the operating margins of the system are very tight, the utility has the flexibility of saying, we're not going to provide you that backup power when you need it for your forced outage if it occurs during that time. But in exchange, the customer gets a lower cost of standby service. And then the final principle with respect to customer options we identified is that customers should have the flexibility to procure standby service competitively from the open market. And so this could apply equally to states where retail choice is available. Obviously, in those types of states, the customer can contract directly with a competitive power provider for standby generation, and that option should be made available. But in addition, in fully regulated states where the utilities are vertically integrated, if there's a robust wholesale market in those states, then customers should be have the option of procuring standby service from the open market through some sort of a buy-through option that's built into the regulated utility standby tariff. So having gone through the background information and discussed the best practices, I'm going to turn it over to my colleague, Jim Selecky, at this point, who's going to go over the specific tariffs that we examined in the study and the recommendations for improvements in those rates that we have identified. Jim?
Okay, Jim, before you get started, Ali, there were a couple of clarifying questions that came in I thought we might address before we hand off to Jim.
Sure.
Could we do that?
Sure, no problem.
Yeah, first one is, on the chart, the graphic that you put up, somebody asked, it looks like the planned outage is occurring during a time when there's a fairly high demand. Is that typical? The asker of the question said that they would think the planned outages would occur off-peak.
Yeah, that's actually true. I suppose in terms of the graphic, that's something that could be improved on that. It wasn't intended to indicate that the planned outage would necessarily occur during on-peak, and I agree that typically what you'd see is the utility would ensure that a maintenance outage would be scheduled during an off-peak period of time. So I agree with that observation.
Okay. A second person asked, why would diversity not also be recognized for lower voltage distribution?
Well, I think that as in terms of costing and the way that facilities are sized, the closer you get to the actual end-use customer, to that customer's meter, the more the utility is going to have to size facilities to reflect the individual loads in that area on a non-coincident peak basis. So I guess the ultimate example would be if you go all the way down to the customer and you look at the service drop, or the distribution lines that are actually running down the street in that customer's neighborhood. If you're looking at a residential customer, then just use that simple example. You need to have those facilities sized in a way that would recognize the non-coincident peaks of those specific customers in that area or that individual customer. But as you get further removed from those customers, you're looking at, say, transmission lines that are designed to move power through an entire segment of the service area or a subregion of the utility service area, then there's no need to size those facilities to serve the sum of the non-coincident peak demands of all those customers, because you're going to end up oversizing those facilities. They're not going to all peak at the same time, so it doesn't make sense to size the transmission facilities that way. Instead, you look at the coincident peak demands.
Okay, and then one final clarifying question. When you use the word prorating, did you mean prorating to reflect daily usage, or simply by equally rating all days in the billing period?
Basically, equally rating all days in the billing period. So if you looked at the overall demand charge the utility would normally apply to a full requirements customer to provide demand for, say, for an industrial facility, in a given month, and you prorate that, divide by the number of days in the month, and create a prorated daily charge, such that if the customer's outage only lasted 1 or 2 days, they pay 1 or 2 prorated days of demand charges. But if they had an extensive outage that, in the extreme example, lasted an entire month, they'd essentially be indistinguishable from a full requirements customer for that given month, and they would end up paying the same demand charge that a full requirements customer would.
If I can interject one thing on that, if the full requirement tariff only requires the demands that are measured Monday through Friday, those are the only demands you would use to prorate the daily demand charge.
No, that's a good point. Yeah.
Okay, great. Well, there are other questions, but I think I'm going to hold the others. Thank you for the questions, folks. I'm going to hold the other questions till the end, and we'll turn it over to Jim now to pick up. Jim?
Okay, as the slide shows, we basically did an analysis looking at 5 different states. We identified within those states a single utility. We ideally were selecting somebody that was obviously fully bundled, and we also wanted to look at some choice. New Jersey offered us choice, and AEP, Ohio Power Company, had both bundled and choice tariffs. Part of the process for selecting the states was we had within the states a meeting, and in 2 of the states we actually had end users participate in the meeting. In the other states, it was essentially between staff members and commissions where we went over our findings and presented our results. If I go on to the next slide. We then went through an analytic process where we were going to basically perform an economic analysis where we wanted to evaluate both the cost to the end-use customer, the CHP customer, under the existing tariff, and what would be the potential cost under our revised recommendation. One of the things I would like to point out that our analysis did not consider or did not reflect any sales back from the end-use customer to the utility. We assumed that the CHP customer was purchasing, was using on-site all the generation. For our analysis purposes, basically we decided, and working with the states, came up with 3 different sizes of loads, basically, as you see in the paper. They're small, medium, and large. That enabled us to at least look at the impacts on distribution, in some instances sub-transmission and transmission systems. In general, we worked with each state to select the size of the customer, the type of load. After we went through a couple of states, some of the other states were in agreement with what we had decided and were willing to use the same kind of parameters that the other states utilized. Next slide. We developed models that on the Microsoft Express sheet that would allow us to calculate the cost that the customer would incur under the current tariffs. In some instances, the revisions were such to the tariffs that the model was just not that flexible without making substantial changes. So for some of the analyses you'll see where we actually calculated the difference or the savings using inputs from a more simplified spreadsheet. But I believe posted on the RAP's website is the models we use for each state. What we had as key inputs, as I list there, is the load factor of the generating unit, the load factor of the load, what is the peak demand, how much of the peak demand was being contributed to by the generation unit, and then obviously all the utility rates, not only for standby, but for any supplemental services and any of the applicable tariffs. And as I said, we modeled the cost both under the existing and the modified standby rates. Next slide, please. What we did when we were making, when we developed our tariff modifications, essentially, we reviewed, obviously, each of the standby components. We reviewed how they interacted with the other provisions of the tariffs or any other riders. We also evaluated this against the best practices that Ali previously discussed, and then we identified and made adjustments to the tariffs. Let's go to the next slide. For those tariff adjustments and recommendations, basically these that are listed here are essentially common throughout all of the states. There were, again, the changes that were made obviously varied state by state, but essentially we felt, as we indicated, that there should be a generation, reservation, and daily demand charges. We believe that there should be seasonal off-peak and on-peak charges, basically for demand if possible, and for energy. Scheduled maintenance, daily demand charges, again, with proper notification, performing your maintenance during off-peak periods or during periods when the utility has enough generation to serve, and scheduling that maintenance, you should receive some type of discount. We looked at the dedicated distribution investment. We tried to reflect in our rates any load diversity associated with the transmission and what we call shared distribution facilities. Generally, the shared distribution facilities are thought of as maybe the distribution substations and sometimes lines in and out of those substations. We also looked at an interruptible rate option. We thought that that should be available, and an open market option if available. In other words, even in a fully regulated state, you could have a part of your tariff an option that allows you to buy standby service in the open market. If you did that, you would essentially avoid the generation reservation charge. As a footnote to that, the two large utilities in the state of Michigan both offer that option, even though they're not fully an open market state. Next slide. What I intend to do here a little bit is at least just touch base and make sure we have some time for questions. What we did in the case, and as I indicated, we basically utilized those principles that I previously outlined on the common tariff recommendations and tried to apply those. When we looked at the Arkansas tariff, the issue we really had is that we thought there should be more rate transparency. And what I mean by that is we thought basically the charges should be unbundled. So the customer could see the generation component, the transmission, and the distribution component. Plus, in the case of Arkansas, the rates relied on other riders. So the transparency, you had to look at the other riders to get loss factors, discounts, and things like that. We felt that if you had more on-peak and off-peak type charges, both for the demand and the energy piece, you would send better price signals. And again, what we wanted to do was increase the flexibility by offering an interruptible rate option, and if possible, we would offer the option where you could purchase your standby from the open market. Also, we wanted better clarity in the tariff, and again, by that, what I meant is, if you look at the report, we did reference in the report one section of the tariff that seemed to be confusing or in conflict, where maintenance could only be performed during the off-peak period, but the maintenance had to be scheduled for at least a day, which means that included the on-peak period. So we thought if making those clarifications would be beneficial. And again, like I said, essentially what we did is we took the Arkansas tariff, we then revised it for our common practices, and developed a standby tariff. Included in the report is a summary and the economic impact of our changes to be made. One thing before I move on, I want to say in each instance, we could not rely, or we didn't rely on a cost of service study. Generally what we did is we relied on the full service or the supplemental tariff to develop our recommendation. And we looked at provisions in the supplemental tariffs to determine what portion was transmission, distribution, shared distribution, and items like that. We go to the next slide. The biggest problem I guess we encountered or we faced with the Colorado tariff is they had a grace energy hour. Grace energy hours provision, and under that provision, essentially, they give you a grace period of about 1,050 hours, which is about 12% of the year. Once that expires and you've had outages in excess of that period of time, you essentially go to the supplemental tariff. We felt you were better off with the generation reservation fee and daily demand and energy charges, as opposed to having to pay a fee or an assessment and having a grace period that was up to about 12% of the year. When we did our analysis for this tariff, we did it on a monthly basis, so it would be easier to recognize and or easier to evaluate and put on a common ground. I realized that this really is an annual tariff. Next slide. The next one we looked at was New Jersey. New Jersey is a customer choice state. It appeared to us, to be very honest with you, that the tariff was really established back in about 2003, I believe, was the footnote at the end of the tariff. So the tariff is more than 10 years old. There were some provisions in it that I just think probably didn't belong. They talked about scheduled maintenance. You got to remember, you're not buying generation, you're buying distribution service from JCP&L. So, you know, I really don't believe that belonged in there, but our mission was to address the various provisions in the tariff. And the tariff did limit the scheduled maintenance hours, and it was actually a function of when the customer took service. In other words, there was a cutoff date, and I don't have it right in front of me, but there was a cutoff date specified in the tariff, and if you came after that date, you couldn't get maintenance service. And I think that some of those were just hanging over from the days when there was bundled tariffs in New Jersey. Also, the tariffs indicated that the tariff wouldn't be available to you if your generator availability factor was below 50%. We didn't believe that provision should be in there. And finally, if you look at those tariffs, you'll see there's a whole series of demand charges that they take a look at. They look at billing demand, maximum on-peak load, annual average generation on-peak, and through the magic of a formula that they came up with the charges. We felt that could be somewhat simplified tremendously by just looking at the distribution tariffs associated with service on the supplemental and full service tariffs and applying them in those instances. Next slide. Ohio was probably one of the bigger challenges, only because in Ohio, and it probably wasn't the smartest thing I did, or we did, we selected Ohio Power. Ohio Power has two separate zones, meaning they had a separate tariff for the Columbus Southern Zone, and ironically, to add confusion, they had a tariff for Ohio Power Zone. Although the tariffs were somewhat identical, were very close to being identical, we basically had to analyze 4 tariffs. 2 of them dealt with bundled service, 2 of them dealt with choices. Our basic problem with the Ohio Power is they had a menu of forced outages. In other words, if you're forced outage, you would, as a customer, pick what you believed was the appropriate forced outage rate. So if you picked a forced outage rate, for example, of 5%, that allowed you, 438 hours for interruptions. It identified the fees and what you would pay. And if you exceeded the 5% forced outage rate, you would go to the full service or the supplemental tariff. And they gave you a menu of forced outage rates that varied from 5% to 45% to 30%. So we just felt, I just felt that a customer in that position probably would be conservative because the penalty was great and might be paying a lot more for standby service than the customer should have been. So essentially we eliminated this menu of forced outage rates and designed our rates based on, again, the common principles, daily demand charges, maintenance charges, and to the best of our ability, on-peak and off-peak charges. Next slide. The last state we looked at was Utah, and that was their Schedule 31. Their Schedule 31 basically did not have a reservation charge. They did have daily on-peak backup charges. So in some regards, the tariff was putting aside the level of the charges, was relatively close to what we had kind of been proposing. What we did actually in this instance is we did create a daily demand charge, and we created a reservation charge also. And actually, when you look at, and the other thing we did is we created summer and winter charges, and again, we used their full requirement rates to help develop those charges. And if you look at the report again, attachment Utah 3, I just happen to have it here, you'll see actually in the winter time, our rates were actually lower, while in the summertime, our rates for certain outages were actually higher. Overall, our rates provided savings. One last thing I would like to say before I get to conclusion is, in each of these instances, we didn't have specific generation data. In other words, we didn't have data about the CHP generators that were on each of the utility systems. So for ease and simplicity, we used a forced outage rate of 5%. If you recall, Ali said that you would apply the forced outage rate to the supplemental tariffs. For purposes of our analysis, we just selected 5%. I've been in cases or in instances where the best generator on the system was indeed below 5%, and in that instance, we would have recommended using that generator's forced outage rate to set the generation reservation charge. And the reason you select that to set the generation reservation charge, if you select a higher number, that generator is helping to subsidize either other generators or other customers. Last slide, please. And in conclusion, our standby rates, again, we think that having standby rates that are fair and equitable, not only to the CHP customer, to the utility, but to the other customers, are essential in developing and providing economic service. I think all the customers can benefit from that. I was recently in a case where the utility was asking to build a new source of generation. In those instances, to make a little bit of a stretch, if the customers can build self-generation themselves, that removes that burden on the other customers for helping to pay for the cost of new generation. And obviously, the things that we pointed out under the existing rates and terms and conditions, we think that there should be a better match of the utility cost, good transparency, provide the CHP customer with flexibility as much as possible without, again, as I said, harming the utility and also harming the other customers. And that concludes my presentation.
Okay, Jim, this is Carl. I wanted to start with a couple of clarifying questions. One of the, you stated a bit ago how you selected the 5 companies, or 5 states that you chose to focus on. Could you, again, briefly just recount how did you choose these particular ones to focus on in this case?
Sure. We worked with, well, I obviously worked with RAP on this. One of the criteria was we wanted to make sure that we would have workshops with each of the states, and we also offered as service after this whole process was done that we would provide assistance up to so many hours if they had any follow-up questions. So as we reached out to the various states, this was a criteria, and I'm going to confess, some of it was timing also. Some states were interested in working right away. That was a high agenda item for them, so we actually selected those states. We also wanted to focus on the idea of having a choice state, having some obviously non-choice or fully bundled states, and some geographical diversity. Did we contact all 50 states? The answer is no. We started contacting states, and once we filled the quota of 5 states, we essentially stopped there. But a big part of it was having the states work with us.
Okay. During your discussion of the different examples for the states and for the corrections that you recommended or the fixes for each state, you sometimes said that this fix was best or that these are best practices. So at the end of your talk, you summarized by saying they're best practices, but someone from various perspectives. But generally, during your conversation, when you said that this was best, was it your belief that what you're recommending is best from the consumer perspective, the utility perspective, the regulator perspective, the participating customer that adopts BG perspective? You could just say a minute, when you say best, what did you mean by best?
Yeah, I guess as I tried to say at the end, what we tried to do is to design rates or revise the rates so they were basically fair to everybody, fair to the existing customers, and again, obviously using best practices. This is what I believe is the best practices. In other words, we felt that the rate should be fair to everybody, that these customers, the CHP customers, should pay their fair share of the cost associated with the service that the utility is providing them. So A, they are not being subsidized, and B, they are not subsidizing someone else. The problem with CHP customers, and I have seen this in cost studies, where some utilities have attempted to put these customers in the cost of service study. And I think one of his questions earlier on was, in 1 year when they attempted to do that, there were no outages during the on-peak periods. So essentially, customers were not allocated any generation costs whatsoever. Of course, that's not what was going to happen, but that's why I think you have to look at what would that customer pay had that customer not had any generation, and based on that, develop fair and equitable rates to all the parties involved. In my mind, what we recommended here represents the best practices. Hopefully that clarifies that.
Okay, great. There's a question. Are you aware of the standby rates pilot program in Connecticut that's aimed at incentivizing CHP? And if so, do you know the status of that program?
Unfortunately, I don't know the status of that program. I just don't know it.
Okay. Another question. Is the discussion we're having today, or to what extent is the discussion we're having today about CHP applicable to other distributed generation technologies, such as rooftop solar?
Generally, rooftop solar, and that becomes that's an interesting situation. Generally, rooftop solar is just obviously, I guess if the power can be used internally. We actually had an instance in North Carolina where the standby rates were actually causing the customer to pay higher demands than he would pay had he not had solar. And the reason for that is that the on-peak demand period was so long that it actually, the solar had shut down and he was paying his normal demand charge as if the solar wasn't there. Yet during the on-peak periods, they wanted the customer to buy standby, and so he was paying an additional demand charge. The problem, and I got to confess, with solar is that what you pay is driven in a large part by the on-peak and the off-peak period. Solar does provide a benefit and to all the other customers, but it's a very tough nut to crack, basically. So sometimes these principles here, you may need flexibility to deal with solar projects. But again, you got to be careful so you're not subsidizing the solar projects at the expense of other ratepayers, unless that's what the regulators want to do.
Okay.
Solar costs is a big problem.
Another question, is interruptible service equivalent to demand response or load shedding?
I would say yes. I think it would be. I think it could be looked at as a form of, the problem with the demand response, generally the hours that the CHP is buying standby service are so limited, it would almost be a stroke of luck that there would be a demand response program there at the same point in time. And again, if the guy's only off, or the CHP customer is only off during the off-peak periods, then it probably doesn't work.
Okay. Could you talk about how standby rates might coordinate with time of use, that is, on and off-peak or seasonal rates and hourly rates?
I guess two things. First of all, I think that standby rates should be seasonable and on and off-peak. That's what the CHP customer buys from the utility. Where if you're talking about the grid and the on-peak and off-peak rates in the grid, that's why we introduced that option where the customer would buy his standby from the open market. We had customers, I was involved in the Michigan case with Detroit Edison. We had one specific customer who was willing, A, to take that chance, and B, believed that his generator would operate efficiently, so efficiently that he was better off not paying the standby, not paying the generation or reservation charge, but would fluctuate hourly with the on-peak and off-peak prices on the market. So, I mean, I think there's two answers to this. One, buying standby power from the utility, we think it should reflect on and off-peak, seasonal and non-seasonal rates for both demand and energy. And if you're buying from the market, you're automatically going to be subject to hourly price fluctuations, because that's how the utilities, or that's how you're going to buy power from the market under that instance.
Okay, great. How would your best practices deal with hybrid generation / energy storage facilities that are becoming more common, at least where CHP facilities may also have storage facility, solar facilities and or storage?
I really kind of, to be honest with you, haven't thought about that. In other words, how, I guess in that instance, wouldn't the only, I mean, for that type of facility, isn't that type of facility only basically storing energy for use during off-peak periods? So isn't there standby requirement? They're using the power themselves, only really minimal. I don't know why they would have a great power need.
The contract capacity for standby in that instance could be adjusted such that it was only whatever was in excess of their storage, their on-site storage capacity. So they wouldn't necessarily need to back up the entire capacity of their on-site generation if they also had storage in conjunction with that.
Yeah, I guess it would work the same way. You're right, Ali, if they were using the storage for their own usage. But if they were selling the storage, take advantage of the market prices, yes. But I would say the standby tariff would work the same if they were using the storage for their own usage. That they would be subject to the same type of standby charges that a normal CHP customer who's burning gas and generating steam and electricity. So I think the charges would be the same. But I got to be honest with you, I've not thought through an example all the way through.
Okay. Great. Well, it seems to me like you're going to get different hybrids, and it may be different for different hybrid combinations with solar and storage. So maybe hard to answer it generically, maybe.
Yeah, and I think that's a good point. That's exactly what happens in a lot of instances. You're exactly right. There are people who are building solar to sell into the system, and there are people that are using it themselves. And you're exactly right. One answer doesn't fit all situations.
Yeah. Here's a more nuts and bolts question. Did you get access to customer utility bills, or did you look at tariffs and assume a customer with so many kilowatts and so many kilowatt hours would have faced such and such of a standby charge according to that tariff.
We did not get access to any customer bills. The only thing we got from a couple of the states was a database that basically showed, and I'm doing this from my memory, showed the size of the generators, and I think it might have had the load at the facility. And I don't even know if they, I do not believe they had any forced outage rates. Basically, no, we got no access to any specific customer bills.
Okay. For a customer who requires more power than they are able to produce using their own CHP, should their generation reservation charge be based on their maximum generation value, their maximum usage from all sources, or some other value?
It should be based on what their generator output is. And the problem with the maximum value is a lot of those units have different ratings for the summer and the winter. So in other words, seasonal ratings are a possibility, even monthly ratings are a possibility. But that's their standby, should be the output of their generator, not the maximum that they would buy from the utility. Does that make sense? If I answer that question. Carl?
I think so. Ali, did you want to add anything, or is
no, I think Jim captured that right. I mean, basically, your contract capacity is typically going to be defined by the maximum capacity of your on-site generation, so that's what should define your standby requirements.
Right. For example, when I talked real quick about the Utah tariff, they had that high charge of, what is it, about $40 of KW, and that really was a charge, and an excess power charge. That charge was basically if you used more power than your contract capacity, and you would have two contract capacities. You'd have one for your supplemental service and one for your CHP unit.
Okay. We only have a few more minutes, and we have lots of questions. So just sort of brief answers to these ones if we can. Did you speak about demand ratchets for the single highest 15-minute peak demand over some prior period, sets the demand level over a subsequent period? Does that approach make sense?
No, we don't believe demand ratchets are appropriate for standby purposes.
Okay. If all of the if the best practices that you recommend were implemented, did you make any kind of an estimate of how much impact that would have on CHP adoption? Is there a megawatt number that you estimated based on that?
No, we didn't do that.
Okay. Let's see. Please explain how the base rate for utility generation capacity should be determined. My predisposition is to ensure that the value of generation capacity provided by all CHP systems should somehow be included in the calculation because the utility does not provide those kilowatts.
I don't understand the question, to be honest with you. I don't understand how that would all be calculated. I don't understand how that would impact the utility. Again,
like that, yeah, I wouldn't think the capacity on-site generation would affect how you allocate or calculate the utilities embedded costs. That's
okay.
The question.
Okay, here's another one. How do forced outage rates and coincidence factor relate? And how do you do the math to reflect the relationship?
The forced outage rate is random, and you know, I guess you're kind of assuming that and I don't know the relationship, because the forced outage rate is a random event, and I guess I don't see how the two are tied together. As I indicated real quickly, in that instance where the utility filed the cost of service for all their standby customers, none of none of them, none of the outages were during the on-peak periods. So it's difficult to make I guess there's 8,760 hours a year. If 1,000 of them are during on-peak, I guess that's your ratio because it's a random event.
Okay. Given the public policies to encourage CHP, has anyone considered basing standby rates on likely levels of CHP penetration over the next decade or so? For example, with higher diversity of generation?
We did not look into that at all.
Okay. Let's see. Here's let me give you one more question. This is kind of a long question. Given that DER is growing at scale and that standby and other DER-related rates are outmoded, what do you think about new frameworks for negotiating DER service agreements that rely less on subsidies? This person says, for example, net metering, and more on real costs and benefits of DER. An aspect of this would be the recognition that DER can provide grid support services, for example, ancillary services in the future.
Anytime somebody deals with benefits, I think it becomes, somewhat arbitrary. We do have, by the way, generators. In fact, we have a client ourselves who has a generator that actually does provide. He sells out, and he actually provides ancillary services into one of the operating systems. So generators can do that, but they have to make that commitment.
That's typically a service that's unbundled and separately priced, so I'm not sure it would interact directly with the provision of standby.
Right.
Okay. Well, my apologies to those whose question I didn't get to. There are a few left on the table, but we're coming to the end of our time. Thank you both, Ali and Jim, very much. We want to thank Oak Ridge National Lab and the U.S. Department of Energy for their support for this project. And this is, part RAP's interest in this kind of project is part of our goal to try to make these tariffs reasonable so that efficient, cost-effective sources of energy are invested in, and that it's done in a way that's fair and equitable to all customers and to the benefit of society as a whole. So, and to the utility as well. Anyway, thank you all for joining us today. I do want to say that the webinar is going to be posted on the Regulatory Assistance Project's website. That'll probably take a day or so. And if you haven't already noticed, the paper and this presentation are also posted on the website. So once more, Jim and Ali, thank you both very much.
Thank you.
Hey, thank you.
Okay, and that concludes our webinar today. Thank you for all of you for joining us. Thanks.